Hello everyone. This is the lecture number 12 in the series of the fluid mechanics. Okay. So in the last lecture we have discussed about boundary condition things. No slip boundary condition and no temperature jump condition, like kind of thing. Okay. So in this lecture we are going to discuss about the speed of sound. Okay. So most of you are having doubts or uneasiness in your mind what we why we are discussing here about the speed of sound. Okay, so most of you are aware that compressibility effects play a significant role in gas flow. Significant density changes caused by the flow. Okay, the density keeps changing in cases of gas. Okay, so that the compressibility become important when the flow velocity reaches a significant fraction of the speed of sound of the fluid. Okay, so what does the speed of sound mean? Okay, so most of you know that a speed of sound in the air is like 304 meter per second and kind of something. So what does this actually means? Okay, speed of sound means. Okay, so that I am going to discuss here the speed of sound. And speed of sound can be defined as it is the speed of sound of a fluid is the rate of propagation. I will write it that will be better. It is the rate of propagation of small disturbances pressure pulse. Okay, so best example is have you seen that when you throw ball in the pond, a wave like kind of things, the circular wave kind of things starts traveling from that center point to the very far distance in form of circular wave. Okay, so in similar things, the propagation of a small disturbance proper pulses wave, or we can call it as a sound waves. Okay, sound waves. Okay, through the fluids. Okay, through the fluid. Okay, so speed of sound is defined as it is the rate of propagation of a small disturbance pressure pulse or sound waves through the fluid. Okay, so I've told you the example, right? When you throw the any rock or anything in the pond, you will see that circular wave is traveling away from the center point. The center point is the point where you throw or threw the stone. Okay, so accordingly that wave will get transmitted, propagate. Okay, similarly when sound waves or the pressure, we can call it as a small disturbance pressure pulse. Okay, sound waves travel through the fluid. Okay, so the rate at which they are traveling is known as the speed of sound. Okay, so from momentum and thermodynamic arguments, the speed of sound is defined by the pressure density derivative proportional to the isentropic bulk modulus. Okay, so we will prove it later on, but I'm just telling you that this is a statement and the formula. Okay, so it is what I'm saying. What I mean to say is a square equal to b by rho, or is equal to dp by d rho of, okay, and k into dp by d rho at constant temperature. Okay, so this is the a is the speed of sound. Okay, a speed of sound in any fluid, and this is b is isentropic bulk modulus. Okay, this s means that is this formula is at constant entropy. Okay, that's why we are saying b as a isentropic bulk modulus. Okay, isentropic bulk modulus, and it is defined as b as a rho into dp by d rho is okay. So when you divide it by rho, it will come as like this. Okay, so that's why I've told you the statement before. The speed of sound is defined by the pressure density derivative proportional to the isentropic bulk modulus. Okay, so that means this isentropic pressure derivative with respect to the uh, density derivative at the constant entropy is proportional to the bulk, and that the constant proportionality is this rho. That's why I mean to say that dp by d rho at constant is proportional to b. Okay, and this rho has come, and from there this formula is have been getting. Okay, so from where we get this formula, the formula we get it from momentum and thermodynamics argument. Okay, and which we will discuss in the upcoming lectures. I mean in the later chapter, and we will I will explain you explicitly, and I will derive this formula. Okay, and this k is nothing but cp by cb. Okay, cp by cb. This t means at constant temperature. Okay, at constant temperature. So at constant temperature, the speed of sound, okay, so we are discussing about the speed of sound here, right? So I mean this a is a speed of sound. So here the a square, the speed of sound in any fluid, is defined as b by rho. Okay, or dp by d rho as s, and k equal to dp by d rho at constant temperature, and k is equal to cp by cb. So all these are defined for, I mean this we have discussed it for the speed of sound at any constant entropy or the constant temperature. When constant entropy is there, we will use these two formulas, and where it is at constant temperature, I mean isothermal, we will use this formula. Okay, so I will write it as isothermal simply here. Okay, so I hope you all understand this. And now I have told you that these things, speed of sound, is mainly useful in for compressibility, right? For compressible fluid, I mean highly compressible fluid. Okay, and the highly compressible fluid is almost approximately to ideal gas application. Okay, so if any fluid is highly compressible, then we can approximate it to as ideal gas. Okay, so I mean we can't do it always, but most time, or to make the problem easier, we will just approximate it to as ideal gas equation. Okay, I mean ideal gas, and in that case we will just use that pb is equal to nRT, right? And p, I mean v. Okay, this n is number of mole is divided by mass by total mass, I mean molecular mass, r into t. Okay, and when you divide p is equal to m by this volume v, okay, into RT, and this is defined as, and this m is here. Okay, and this we call it as a universal constant r, and overall it is known as gas constant. Okay, we have discussed it earlier. Okay, so if you don't get it, please watch the previous videos. You will get that this r by m is known as r gas, I mean gas constant, and this r is universal constant. I think this r we have earlier we discussed it at k, so denotation doesn't matter, that's concept. Remember the concept. Okay, so now we will write as p equal to rho r gas into t. Okay, and when we will just dp by d rho, so it will become r gas t. Okay, okay, so we can write it r k r t. Okay, so now we know that a square, I mean the speed of the sound, is equal to dp by d rho at constant entropy, right? And we find it out for ideal gas, that dp is equal to kRT. Okay, derivative of pressure with respect to the density is kRT for case of ideal gas. Okay, we are dealing with for ideal gas only. Okay, remember that. So we can find it out that for ideal gas the speed of sound is kRT. Okay, kRT. Okay, so now you have seen that for ideal gases the speed of sound, I will write it here, the speed of sound for ideal gas. Okay, and you see that r and k are constant, so a speed of sound for ideal gas only depends on only depends on temperature, right? So when you increase the temperature, the speed of sound in the ideal gas will increase, and when you decrease the temperature, the speed of sound in the ideal gas will get decrease. Okay, so for example, just for instance, I'm taking air at 20 degrees Celsius. I am assuming air at as a ideal gas. Okay, so in that case, the speed of sound is the speed of sound. Okay, I'm just using, remember that I am using the approximation that air is an ideal gas. Okay, approximation as ideal gas. Remember that this is a very, I mean, important observation. If you don't observe it carefully or don't understand it completely, you will just use absolutely everywhere that speed of sound is like that. Okay, no, we can't try to use that. So the K is 1.40 for gases, and R is 298, sorry, 287, right? 287, and multiplied by 293. 293 is the temperature into Kelvin. Okay, and the velocity will come as 343 meter per second. Okay, so we take it like that. Okay, 340 meter per second for solving problems in our high schools or in the class 10th. Okay, so we can say that if in this case the air velocity reaches a significant fraction of a, I mean a speed of sound, we can say that 100 meter per second, then we must account for compressibility effects. Okay, otherwise we can ignore that compressibility effect. Okay, so when it's reaching to, I mean when for example we are taking that 100 meter per second, so it's like almost one third. Okay, so it's not it is just a safer idea that before that, I mean whenever the speed of air reaches to 100 meter per second, we will just assume the compressibility effect. Okay, that means the whenever the speed of sound, I mean whenever the speed of air reaches one third of the speed of sound, right? A speed of sound, we can assume or we can say that I mean include compressibility effect as well. Okay, whenever you are solving any problem or anything. Okay, compressible effect. Okay, now we can define these things in other ways around, and that is with the help of Mach number. Many of you have known already, because these things are getting taught in our school days as well. So the Mach number is defined as ma is equal to b by a. Okay, so I mean what is b and why it is a. So v is your speed of air and a is your speed of sound in air, or here I am taking for example air, but this can be any fluid. Okay, so in that case I've told you that the criteria that is following for considering compressible effect is 1/3. So here we will take that if ma is greater than 0.3, almost approximately greater than 1/3, we will say that include compressible effect. Okay, when it's not, I mean when it's greater than, I mean less than 0.3, we can ignore. Okay, can ignore compressible effect. Okay, and whenever it is greater than 0.3, we cannot ignore this compressible effect. Okay, we have to consider that. Okay, and we will solve the problem accordingly. Okay, so I mean most of you have understood what the Mach number means and what's the importance of this speed of sound, why we are discussing it here. Okay, so one more topic left for the first chapter in this fluid mechanics, and after that we will conclude the chapter 1 by solving some of the problems from the GATE or ESE or from the bookish problems as well. Okay, so till then keep learning and goodbye. We will meet in the next lecture. Okay.